Three relatively straightforward topics: venous return, Starling's law, and cardiovascular drift that are actually linked a little bit together. First of all, venous return, which is the amount of blood returning to the heart. Dead straightforward definition. So the blood that's been round the body, being pumped around to the muscles, etc., then has to work its way back through the veins back to the heart. The potential problem with venous return is a lot of that blood has gone down into the lower legs, for example, which is far away from the contraction, so it's started to travel a lot slower. Also, it's got to, if in most sporting situations where we're in a standing position, it's got to work against gravity as well, so it's going to be struggling to get back to the heart with any real pace. Therefore, what can happen in that situation is what we call blood pooling. Blood pooling is when the blood pools in a certain area in the body. We often associate this with sitting on an aeroplane for a long time, which is why you would have to get up and move around to prevent that blood pooling usually in your lower legs and your calves. So a common question around venous return is the mechanisms that assist the return of blood to the heart, in other words, venous return. So because of those potential problems, we need to get round that, and so these are the solutions. The two main solutions really are the skeletal muscle pump, which is the fact that you can see over here that these muscles contract. Alright, so the muscles contract and squeeze against the veins here, and therefore they tend to squeeze the blood upwards. So you can see that here the blood moves up like that. Linked with that are the pocket valves. So again, you can see here the valves over here that they're able to shut, and that prevents this blood going backwards. So when the muscles are relaxed, which you can see here, then the blood would tend to drop down over, but then the pocket valves shut and we get that, and the blood just stays where it is. So then we get another contraction over this side, and the blood will then squeeze up again. So as well as this, within the vein we get a layer of smooth muscle, which also has the same effect. It's able to do a little bit of contracting within the muscle, not within the muscle, the smooth muscle within the vein itself, so it's able to squeeze the vein from within itself. The respiratory pump, which is the action of the lungs contracting in the thorax and therefore doing the same sort of a job as the muscles in the legs. So the blood in and around the chest area is getting squeezed back to the heart, which is obviously quite close anyway. And lastly, the suction pump of the heart. So as the blood gets back towards the heart has a suction pump which just sucks it in that last couple of seconds. So Starling's law, again a fairly straightforward concept, and one that if a little bit of common sense is applied, then you'll understand it. So Starling's law suggests that basically that stroke volume is dependent on venous return. So we now know what venous return is, the amount of blood that returns to the heart. We know that stroke volume is the amount of blood that the left ventricle pumps out per beat. So it's fairly obvious that the amount that we pump out is dependent on the amount that returns. So if venous return increases, in other words, we get more blood into the heart, then stroke volume would also increase. Alright, so with an increase in venous return, stroke volume will increase as well. That obviously can be the opposite. So if venous return decreases, if we're stood still, for example, and venous return therefore decreases, then it's obvious that stroke volume will also decrease. So as we stand, heart rate would have to take over a little bit more than stroke volume. So that leads us on to cardiovascular drift. And cardiovascular drift occurs during prolonged exercise, so long periods of exercise. So this on here, going along the axis here, this would be time, so this would be a long, so if we're going for a run of 30 minutes or more, and you can see that we've got a couple of values up the side. We've got heart rate, which is on the red line, and we've got stroke volume, which is on the blue line. The other thing that should be added there really is that cardiac output. So cardiac output in this instance, as we go along the run, would increase slightly, which I think is fairly obvious. In order to keep up with that slight increase in cardiac output, we can obviously do that in two ways, being as cardiac output is made up of heart rate and stroke volume. So we can either increase heart rate or increase stroke volume, or both. So it's just worth knowing that how we do this. So initially we can see that the initial gains in cardiac output are made up from stroke volume. So this is to do with the ejection fraction. We start to emit the full amount of blood that's in the heart. So at rest we don't do that. The ejection fraction isn't at its maximum, but we can easily start to do that and pump out the 100% or thereabouts of the amount of blood that's in the ventricle at any one time. So that's why we increase stroke volume initially. We can see, however, that there comes this point here that stroke volume goes down, and therefore heart rate increases. So this is the concept of cardiovascular drift. So this is the first point that you would need to make on a cardiovascular drift question, is that stroke volume decreases and heart rate increases. So it's this point here that we can see. You need to be able to explain why though. So this comes down to the fact that during that prolonged period of exercise we start to sweat, and we know that the body does this. We start to sweat in order to keep us relatively cool, but because of the sweating we are clearly losing fluid, and a lot of the fluid that's in the body is actually in the blood and in the plasma and stuff. So we lose fluid from the blood. This makes the blood become more viscous, or basically thicker. Alright, so more viscous means thicker. So the blood, because it's losing fluid, becomes more thick, and therefore viscous. The fact that it's thicker means that the blood travels around the body slower. So it takes a little bit longer to get round. Now that has an impact directly on venous return. So therefore venous return will slightly decrease. And knowing what we now know about Starling's law, that stroke volume is dependent on venous return, if venous return is decreased, then also stroke volume will decrease. And this decrease in stroke volume, because of this, means that heart rate needs to take over. So this is where we get cardiovascular drift, where stroke volume decreases and heart rate increases.